So let's start with the next solved example. Find the minimum and maximum values of the quadratic polynomial fx equals 5 minus 3x minus 2x squared. Of course, x belongs to the set of real numbers. So we are looking at a real polynomial. So how do we proceed with this? The first thing is to look at the value of a. So if we compare this to a standard quadratic polynomial, ax squared plus bx plus c, you would notice that the value of a in this specific example is a equals minus 2, which is less than 0. So immediately you know the parabola associated with this quadratic polynomial opens downwards. The next thing to check is the discriminant d. So if you were to compute d, which is b squared minus 4ac, so that equals minus 3 whole squared minus 4 times 5 times minus 2. So minus 3 squared is 9, and this is plus 40. So this is 49. So this is greater than 0. So you know that the parabola intersects the x-axis at two distinct points. So if you were to have a mental sketch of this parabola, it would be like this. So a is less than 0, so it opens downwards, and there are two distinct roots for this quadratic equation because the value of the discriminant is greater than 0. So once you have this, you are looking for the maximum and minimum values of this quadratic polynomial. So clearly, because a is less than 0, we know that this point is the maximum. So this is also the vertex. And with regard to the minimum value as such is not defined because it is unbounded. If you go to plus infinity or if you go to minus infinity, this curve is going to go on and on and on to minus infinity. So the minimum value of this quadratic polynomial is not defined as such. So how do you get the maximum value? There are two ways to do this. We already derived the result for the coordinates of the vertex, which was just minus b over 2a comma minus d over 4a. So you could use the result straight, or if you were to not remember that result, it is also straightforward. You can take the derivative of this and set it to 0. So df dx would be minus 3 minus 4x, and if you were to set this to 0, this will be at the max value of x. You would see that x max equals minus 3 over 4. And then you could also compute the maximum value of this. So f max would be f at a value of minus 3 over 4. So this would be 5 minus 3 times minus 3 over 4 minus 2 times minus 3 over 4 whole squared. So I leave it up to you to evaluate this and find out the actual the maximum value. The other point is that the minimum value is not defined as f of x approaches minus infinity when x approaches either plus or minus infinity. So the minimum value of this quadratic polynomial is not defined. So the next problem I want to show to you is one which requires fairly little bit of quick thinking, and recognizing the patterns in terms of a quadratic function and a quadratic polynomial. So the question reads as follows. If ax squared plus bx plus c equals 0 has no real roots, and of course you are given that a is not equal to 0 and a, b and c are all real numbers, then comment on the sign of these. So comment on the sign of the first quantity I want you to look at is 4a minus 2b plus c times 4a plus 2b plus c. Second quantity I want you to look at is a times 4ac minus b squared. The third quantity I want you to look at is a times a plus b plus c. So we are given that ax squared plus bx plus c equals 0 has no real roots, given a not equal 0 and a, b and c are real numbers, and we are asked to comment on the sign of this quantity here, and lastly a times a plus b plus c. So if you want to just look at this problem, you could be lost. Okay, how do I start with this? I have this quadratic equation and I know it has no real roots, which means that the discriminant has to be negative, and I don't know the sign of a as well. So the only thing you know from what is given here is that the discriminant is less than 0. So you know that d is less than 0. So b squared minus 4ac is less than 0. And you look at this and see that, okay, 4ac minus b squared appears here. So at least you know the value of one of the terms here. But what about this term here and this term here? And this is where you start to you have to start to recognize patterns in these polynomials. So the first thing to realize is, if I denoted ax squared plus bx plus c as fx, then immediately if you were to substitute 1, so f of 1 is just a plus b plus c. F of 2 is 4a plus 2b plus c. And f of minus 2 is 4a minus 2b plus c. And then you see that the quantities which are appearing here, they are nothing but f of 1, which is here, f of 2, which is this, and f of minus 2, which is this. So at least now you know what these quantities are representing, and you can try and make some sense out of it. So the other thing we know is that d is less than 0. There are no real roots. So either fx is always positive when a is greater than 0, or it is always negative if a is less than 0. So let's make two cases to solve this problem. So case 1 is when a is greater than 0. So we know if a is greater than 0, and because d is less than 0, fx is greater than 0 for all values on the real number line. So meaning that f of 1 would be greater than 0, f of 2 would be greater than 0, and also f of minus 2 would be greater than 0. So therefore, in this case, when a is greater than 0, f of minus 2 is greater than 0, f of 2 is greater than 0, meaning that the product of these two would also be greater than 0. So f of 2 times f of minus 2 would be greater than 0. The other hand, so let's do case 2. So when a is less than 0, then f of x is less than 0 for all x belongs to the real number line, meaning that f of minus 2 would be less than 0. So would be f of 2, meaning that the product of these two would still be positive. So f of 2 times f of minus 2 would still be greater than 0. And therefore, we have covered all the cases. So when a is greater than 0, this thing is positive. When a is less than 0, the term is still positive, meaning that for all possible cases, 4a minus 2b plus c times 4a plus 2b plus c, it is greater than 0. So now I leave it up to you to solve parts B and part C. So again, you have to recognize that a plus b plus c is nothing but f of 1, and you know that you can do these two cases. And similarly, 4ac minus b squared is negative of the discriminant, so it should be positive because we know that the discriminant is negative. So with this, I'll stop focusing on this example, and let's just do let's just partly do one more example so you can have a better feel of what kind of questions are possible. So the next problem reads as follows: if f of x equals x squared minus k plus 3x plus 5k is always positive, for all real numbers, comment on the values of k. So again, the way to solve this problem is to realize that if any given quadratic polynomial is always positive, then that is only possible if a is greater than 0, that is the coefficient of x squared is greater than 0 and the discriminant is negative, t is less than 0. So we know that a equals 1 here, which is greater than 0. So the first condition is satisfied. The second condition is that d equals b squared minus 4ac should be less than 0. So what does this mean? So b is minus k plus 3. So minus k plus 3 whole squared minus 4 times 1, which is a, times 5k should be less than 0. So this is k squared plus 6k plus 9 minus 20k should be less than 0. So this is k squared minus 14k plus 9 is less than 0. So we started with this inequality. We knew that x squared minus k plus 3 times x plus 5k is always positive. And in this problem, when we tried solving, we reached a condition which is another inequality. But this inequality only involves one variable. So there we had both x and k, whereas now we have, based on the properties of the quadratic polynomials, we have reduced it to a problem or an inequation which only involves the variable k. So now we know that this condition must hold for all values of x. So for all x belongs to R. So this condition is holding, or actually, sorry, this value should hold for all values of k, or we want to solve for those values of k for which this inequality holds. So let us find out the roots or the discriminant of this equation in k. So if we were to find out the discriminant, so d would be equal to minus 14 squared. So b squared minus 4 times ac for this particular equation. So this is 196 minus 36, which is 160. So this discriminant is positive for this equation, meaning that it has two distinct roots. And I'm just going to state the roots here without solving for this equation. So you can use minus b plus minus root d over 4a. And you would see that the roots are k equals 7 plus or minus twice square root of 10. So if you were to visualize this parabola here, or the parabola corresponding to this quadratic polynomial, it would look something like this. It would intersect the x-axis at 2 points. And remember, the left point is always the one which is the smaller root. So this point would be 7 minus twice of root 10 here. And this point would be 7 plus twice of root 10. Therefore, the region we want is the one where this quadratic polynomial is less than 0, which means the solution we are after is k belongs to 7 minus twice of root 10 to 7 plus twice of root 10. So the solution of this problem is those values of k for which x squared minus k plus 3 times x plus 5k is always positive are those real values or those real numbers which lie between 7 minus twice of root 10 and 7 plus twice of root 10.